What if you could teach AI to trade the stock market for you? And not just trade, but potentially trade smarter and faster than ever before. In a previous video, I laid the groundwork by successfully connecting a cloud-based Python app directly to my Interactive Brokers paper trading account, a crucial proof of concept, and then implemented a very simple trading strategy. But simple was just the start. Now we're going to take a leap, and I've got $300 in Datalore credits, and I have access to some of NVIDIA's top Tensor Core GPUs and a powerful $200 per month stock data feed. What is the mission? It's to see if we can harness this cutting edge tech and these powerful GPUs and sophisticated AI techniques to train an intelligent trading system and build a bot that might actually have an edge. So can AI actually help us build a working, profitable trading bot? Typically in my videos, I'll try to do things where you guys can follow along with me with free tools, but this video is going to be a little bit different where I'm using some of the better and more expensive premium tech to try something new, and I'll include a link to a copy of the code that I create in this video and the links to the resources you would actually need to implement this yourself and follow along with what I did. But this is going to be more of a showing style video. So I'm going to get you up to speed with where we are right now and basically where I had left off on a previous video. So right now we're using a tool called Datalore, which is actually the sponsor of this video, where we're using a Python notebook in this cloud-based software to connect to Interactive Brokers Trader Workstation, where we have a paper trading account with roughly $1.07 million fake money. And the reason I'm using a paper trading account is because it's not real money. So I can try to build these systems, run them, and then see what actually happens without any real money on the line. It's basically just a safer way to get familiar with everything. But because this is a Python notebook in the cloud through Datalore, and this over here, Trader Workstation, is running locally on my computer, I need a way to connect them together. So to tunnel them together, I can open up my command prompt and I can just run this line of code right here. And this is going to form a tunnel that we can use to connect from the cloud to this local application on our computer. And in my notebook, which you can copy using the link in the pinned comment or the description, I've got information on how to get up until this point. And information about like how to connect the tunnel and stuff like that. So right now, we're just gonna go ahead and run this code that I've already created to connect to Trader Workstation. And one thing I'll point out is that everywhere in this video, I've used AI to write the code to do these things. And so it'll tell you what section we're in and then the prompt that I used to have the AI write the code. And Datalore has a little inbuilt AI assistant where we can ask it, where we can put the prompt in there like this. I'll copy with Control-C, paste with Control-V, and then if I run this, it'll give me some code that looks just like this. So anyways, we ran the code that we already had from a previous video. We can see that we successfully connected to Trader Workstation, and that's step one. So now we can just test our connection by seeing if we can get the server time from this software up into the cloud. And we run that, and we can see we got our server time. Now we're just gonna do something very basic, which we're going to just test it out and enter a buy order. We want to see if we can enter this order with Python in the cloud and have it pop up in our portfolio. So right now our portfolio has NVIDIA in it, and NVIDIA is our only holding besides cash. And we have 2 shares of NVIDIA that we can see right here. And so we're going to try to make it go from 2 to 3. So I'm going to run this. And we can see, boom, we can see it bought. So that BOT means bought 1 NVIDIA at this price. So now we have 3 shares of NVIDIA. Now let's scroll down, and I'll point out that sometimes you'll see some red text like this. This doesn't mean that there's some catastrophic error that happened, and sometimes you can just ignore it. And so now we see enter a test sell order. So we want to see if we can sell that share of NVIDIA we just bought. So we want to make this go from 3 NVIDIA shares down to 2. So let's go and run this code, and we can see it instantly executed, and we just sold 1 share of NVIDIA at this price, and now we went from 3 to 2. So we're up and running pretty well. Now we're going to quickly connect to our premium data source. And so what I'm going to be using is this product Polygon.io, And I'm actually using this most expensive one because it has something that I want to use, which is it has minute aggregates and it streams real-time data. So I want to basically go back for several years and look at every minute the price of NVIDIA, every single minute for several years, and then see if we can put that data into an AI model and have AI trained on that data and see if it can find some sort of strategy that could predict how the price is changing. And then we can use the real-time data to attempt to stream that data in and have it make decisions based on what it saw from that minute data in the past. And that's the plan. And I can put a link to the pinned comment in the description for this data source if anyone's curious or they're trying to follow along with this. So I've already written the code to connect. I just have to put my key in and I'm going to run this. And don't worry, I'm going to change my key by the time this goes public, so don't even try using this one. So we've set that up. So now our key is set up, and now we're going to run this to try to import some of our necessary libraries. So we've got those, and then now we're just going to make sure that our API is configured, and we can see that our key setup is complete and we've successfully connected. So now we can implement a very simple trading strategy before we get into our more complex stuff, just as a proof of concept. So what we're going to do is we're going to want to create a strategy where we're constantly taking the price of NVIDIA every second, and we're going to create a moving average that is a 20-second moving average of the price over the last 20 seconds, and then a moving average that is the 50-second moving average over the last 50 seconds. And we're going to make trades based on how those interact with each other because we want to try to gain on momentum. And I'll show you what we mean when I run this. So let's just run this code, which is going to generate some of this simple logic. Now, one thing with this API is to stream that real-time data, we need to connect to this WebSocket. So I've already wrote all this code, which is going to be freely available for download. So I'll run that. Now we've run that. And now I'm going to show you with this visualization function, really what we're doing in this very simple strategy. So we've initialized this function, but we haven't run the visualization yet. Now let's actually go ahead. Now let's start the system. And then we're going to run this code, which is pretty complicated, which is going to actually monitor the trade signals, telling us when we should buy and when we should sell, or when our bot should buy or sell. So we've initialized all of that. Now this is where I'm really going to explain this very simple strategy. So let's actually run the visualization with real-time data. So right now, what we're doing is we're pulling in second by second NVIDIA prices, and then we're going to calculate a moving average. So basically an average of the last 20 seconds of the price of NVIDIA, and then an average of the last 50 seconds of the price of NVIDIA. So the green dotted line is going to be the average of the last 20 seconds, and the red dotted line is going to be the average of the last 50 seconds. Let's let this update one more time, and then so pause it, and I'll show you what we mean. So this blue line is NVIDIA, then we're taking these averages. So whenever we see the 20-second moving average cross below the 50-second moving average, we would say maybe based on momentum that this would be a signal to sell, right? Because the momentum is moving down. Whereas whenever the moving average over the last 20 seconds crosses above the moving average over the last 50 seconds, we would say maybe this is a signal to buy. So we see this little green arrow on the price when we're thinking about selling, and a little red arrow on the price when we're thinking about buying. And this is our very simple strategy. I haven't even tested it at all, and so I have no idea whether that would work whatsoever. It's just a basic proof of concept. And then the rest of this video is where we're going to try to make AI train on past data to see if we can actually come up with something that might actually work. So now this is where we might run this system to see how it actually trades. So let's make sure to establish our connection. So we've run that, and now we're going to start this listener thread in the background. So we're going to give it the opportunity to begin trading. And so now we can see that it just signaled a buy. So it went from 2 shares up to 3 shares. It doesn't allow it to trade for 10 seconds. So if we placed an order, then it has to wait for 10 more seconds to place another order. So then finally, we just bought again. So probably what happened in that 10 seconds where it wasn't allowed to trade was the line dipped under, and then it went back above. But when it dipped under, it was in that 10-second restriction period where it couldn't trade. So this is a very simple strategy. It definitely doesn't work because every time we make a stock trade, we have a $1 commission. And because we're just buying and selling one share at a time, we're just incurring that commission. And so basically every time we're doing a trade, we're just like losing $1 right now. So this strategy is not going to work the way we have it set up. Now let's go and try to figure out how to set up a strategy that will work. Now that we've set up our basic proof of concept and proved that we can make some trades with an algo bot, let's go through a 5-step process to see if we can come up with a strategy that might actually work. Step 1 is to define the AI's goals. First, we need to be crystal clear. What exactly do we want our AI model to predict? Are we predicting the price will go up or down in the next minute? By how much? Defining this target is critical, and we can do step 1 right now. We're going to say that we want to make our AI figure out if the price is going to go up or down from 1 minute to the next. Now, with step 1 out of the way, let's move on to the next 4 steps. Step 2 is that we need to gather and prep historical data. We're going to dive into that premium stock data feed. We'll pull years of historical minute-by-minute data to train our model. We need to clean it and engineer relevant features, things like short-term returns, volatility, volume spikes, etc., features that our AI can actually learn from. Step 3 is to train the model using the NVIDIA Tensor Core GPUs. This is where our AI credits actually come in. We'll train different machine learning models, maybe starting with some powerful tree-based methods, or even jumping into neural networks to find patterns in the historical data and learn to predict our target. Step 4 is that we're going to backtest rigorously. Before risking even our fake paper money, we must backtest. We'll simulate how the AI's predictions would have translated into trades historically and see if the strategy actually shows promise. And finally, step 5 is to integrate and paper trade live. If the backtest looks good, we'll integrate the trained AI model into our existing cloud application. It'll analyze the real-time data stream and make predictions, generate signals, and execute trades through our interactive broker's paper trading account. Now that we know what we want to do, let's hook up to one of these more powerful GPUs. So I'm going to go up here to run, and then I'm going to hit change machine and more details. And so what we can see here is that each of these credits is worth $1. So I started off with 300 and I burned, basically $3.50 worth just playing around on the cheaper machines. So we're going to switch to one of these more powerful machines that gives us access to some of these NVIDIA Tensor Core GPUs. And that's going to allow us to train this data better. So we can pick any of these and we can basically see how many hours I can use them for. Like this one all the way down here would basically mean that I can use 8 of these most powerful GPUs all at the same time for 20 hours. But let's just start off. Let's start off with a less powerful one. Maybe we'll go with this, I guess M probably stands for medium. So let's hook up to this and hit OK. And now it's going to have to start and stop our machine again and reset everything back up. And so you can see everything's basically initializing again. Let's go ahead and reconnect to our trader workstation once this is up and going. So I'm going to copy that back into my command prompt and get our connection established once more. So now we can see that it switched from starting and then now it's on idle. So we're hooked up. Let's just make sure that we can connect again. So let's run this and successfully connected to TWS. Let's just test to get the server time. Boom, perfect. Let's try a random buy order just to make sure it's working. And good, we bought one and now we went from 5 to 6 shares. Perfect. So let's reestablish our connection to our data API once more. So I'm going to run these one more time and we can see that we're now connected to our data API Polygon. So from here, our first step is going to be that we want to retrieve training data, and I gave it a prompt, and basically what we're going to tell it to do is basically start from today and then go back to the last 2 years and pull in every single minute of trading data for NVIDIA for that entire period of time. So we've used in the AI this prompt right here to write this code, and now let's go ahead and run this code. It's taking a few seconds to run because this is a lot of data that it's actually retrieving, minute by minute data for several years. Okay, took 14.5 seconds, and we can see that we have got all this data. So basically we got data for NVIDIA starting from, for me, this was actually yesterday, the 7th of May from 2025 all the way back to 2023, 2 years earlier. And we can see that we actually got 440,000 rows. So that's every minute of data. And the way that it's going to look is going to be like this, where we have an open, a high, a low, a close, the volume for that minute, and then the volume weighted average price for that minute now, and also the number of transactions that happened and some timestamps. So is this enough data? Can we just look at this past data and predict future prices? I'm not sure. So I'll tell you where I'm at with this. I'm expecting to fail. I'm expecting to use these credits and not find anything. And I will be pleasantly surprised if we actually find something that works. So, you got to set the expectations low so that you're never disappointed. And just for fun, I looked up the cost of this machine that we're running. So we're using this NVIDIA A10G Tensor Core GPU. However, we're looking at one that's got 32 gigabytes of RAM. So I went and just looked at some websites and found even the versions of this with just 24 gigabytes of RAM, if you wanted to buy them new, are like $9,000. And I looked at that on multiple websites. So that should give you some idea of why we're using Datalore and renting our time with these things in the cloud rather than just buying the hardware outright, because I do not have the budget to be buying something like this. All right, this next step is crucial. Preparing the data for our AI model. We take that raw historical minute data we downloaded and engineer features. These are like signals derived from past prices and volume, things like recent returns, moving averages, volatility, etc. We'll also define our target, exactly what we want the AI to predict. In this case, whether the price will go up or down in the next 5 minutes. And then finally, we clean it up, getting it ready so the AI can learn the patterns between those past features and the future outcomes. So why don't we go ahead and run this code and look at our outcome. Okay, let's show all. So we can see that there were some non-applicable values that were removed. So we dropped all those NAs, or NANs, I should say. And then we can take a look at basically some new features that are being created with this code. So wherever you see this number and then an M, that means that there's going to be a certain number of minutes looking back. So this would be the return over 1 minute. This is the return over 2 minutes, the return over 3 minutes, return over 5 minutes, etc. And then we're going to do the same thing with simple moving averages over a certain number of minutes looking back, the volatility over a certain number of minutes, etc. And then these will become some features. Whenever you see something like future close or future return, that's basically going to look forward into the future. Same with target. So at that point in time, what happened in the future after that. Whereas the rest of these should be historicals, what happened in the past. And so I think what we're going to be doing is basically looking at things that happened in the past and then comparing them to what happened in the future to see if we can establish some type of relationship between these features. Okay, we have our features. Now we need to prepare this data for the model. Let's be clear on our target, right? So we have this target right here. What we're asking the AI to predict, in this case, it's simply, will the stock be higher 5 minutes from now? Yes or no? Now we need to prepare this data for the model. We can't train and test the AI on the same data. That's like giving it the answers to the test beforehand. So we split our data set chronologically, keeping the time order intact. We create a training set for the model to learn from, a validation set for the model to fine tune, and then finally we'll create a third set, which is the test set, using the most recent data the model has never seen to see and get an honest grade on the model's overall performance. So that's why we see here in our prompt, we're asking it to create X training data, Y training data, X val data, which is the validation, Y validation, and then X test and Y test. So let's go ahead and run this code to split our data set. So we can actually see the results here. So we see that it split them into the training set, which is going to have this many observations, 308,000, and then the validation set and the test set will have 66,000 each. Now that's going to go in line with what we asked up here, where we wanted to put 70% of the observations into the training set, 15% into the validation set, and then the remaining by default would be the last 15% that goes into the test set. And then keep in mind, when we see X and Y, X is going to be the independent variable that we're trying to predict, and Y will be the dependent variables that we're going to try to use to predict X. This is where I think things will get a little bit more interesting. So I've got some code here that's just going to test that we are properly connected to the Tensor Core GPU. So then we can go ahead and start training our model. So I'm gonna run this, and really if we just get a green check mark at the end that says that the Tensor Core was enabled successfully, which we see right here, we should be good to go. And this is not something we have to worry about. So now here's where we're gonna train the model. This is the fun part. So now that our data is split into training, validation, and test sets, that's great. But before we can feed this into our neural network, we need one quick preparation step, which is feature scaling. This just puts all our different input signals like returns, moving averages, volatility, onto a similar numerical scale. So this is really going to help the network learn more effectively. Then comes the exciting part, where we're going to finally train this AI model. We'll define a simple feed-forward neural network and feed it our scaled training data, which is the features we created and the target up or down signal that we want it to predict. This is where those powerful GPUs are going to kick in, crunching the numbers and helping the model learn patterns by seeing the historical data many times over multiple passes or epochs. We'll watch its performance on the separate validation set during training to see how well it's learning to generalize and predict those future price movements. So one thing I want to point out really quick before we run this and start training the model is that one thing we've defined is, so we have these epochs and we're setting this to 50. So basically we're going to process this data in 50 different passes, and then with each pass, ideally we would want it to become more and more accurate as the model gets more time to tune itself with more data. Then we're going to define a batch size of 128. So there's going to be batches of 128 minutes of data. So each batch has 128 minutes of data. So I'm going to run it and then I can talk you through what the output means. So let's run this. And now we can see it's already starting, and it started on the first epoch. So it says epoch 1 out of 50, and there's 2,409 batches. So there's 2,409 separate batches of the batch size that we defined, which was 128 minutes. Now what we can see is that this epoch took 18 seconds. And we declared that we would allow it to run 50 of these. So this might take several, could be more than 10 minutes. So then we can see that there's various information about that. So we can see there's this loss on the training data of this value, and we prefer a lower amount. And the accuracy on the training data was this high, so just barely better than a coin toss at 50.73%. Then, so we can see that both these two, this loss and this accuracy, these were on the training data. But then, if we look over to the right, we're going to see val loss right here, and then val accuracy. So this is on the validation set. So this is actually more important because it's telling us how the model's performing on data that wasn't in the training set. So it was trained on certain data, and then it's seeing this out of the training set data and seeing how it really performs. So what we're actually going to be probably most concerned with is this val accuracy right here. So we can see we're performing at about 52% on the very first epoch for that val accuracy. Then you can see a second epoch is analyzed, and a third one, and a fourth one. And so with each of these epochs, it should get slightly more accurate each time. That's what we would hope for, because basically the neural network is learning and training itself. It keeps processing more and more batches of data to hopefully become more accurate in predicting the data that it didn't train on. So we can see that it's, it originally started at 52%, then it gets to like 52.27%, then 52.33%. Unfortunately on this one, it took a big step back. Then it became more accurate. So over time, this should become more and more accurate, and it should become better at actually predicting whether the price will go up or down in the next 5 minutes. However, there's only so much that can be gained by training. So it might end up getting to the point where the model notices that it's not actually becoming any more accurate, and at that point it will terminate itself. It will stop training new epochs because it wants to avoid overfitting on the training data. So I'm gonna go grab a drink. We'll let this thing train for a little bit and come back once it finally stops itself. All right, so our model just cut itself off. So it went through 34 of the 50 epochs, and then it decided that it was just going to optionally stop itself because it wasn't seeing any more gains in accuracy, and to prevent the overfitting of the model beyond that point. So at the very end, we see the information for this model is that it was accurate about 52.53% of the time, and it had a validation loss of 0.6909. Now, what does this mean? Well, a validation loss of the natural logarithm of 2 would just be purely binary random guesses, coin flips essentially. So if you can get it to be lower than the natural logarithm of 2, so 0.693, you're better than a coin toss. So we did get that. We were slightly lower, but we're not that much lower, right? And if you can get your validation accuracy to be higher than 50%, you're slightly better than a coin toss. That's nice, but it's probably not enough because there's other things we have to consider when we're trading, right? There's commissions from your broker, like we're using interactive brokers. So we need to be correct more than 50% of the time, enough to exceed the commissions and the bid-ask spreads. And another thing we haven't even considered is how much do we gain when we gain versus how much do we lose when we lose? Maybe the losses are bigger than the gains. So this doesn't really tell us enough. So you need to reach a certain level of accuracy based on those other factors to get to a model that might be accurate enough to actually be profitable. So what I would want to target in this video, I would be happy if we could get a model going that was a validation accuracy of 55% or better. That might be my target. So now what I'm going to go and do is try to mess with the parameters and the model we're using and the inputs and try some different things and keep running this, use up some of our credits that we bought over here to see if we can get a more accurate model. And one other thing that we can do to see the accuracy of our model as it was changing over the history as we did these different epochs, we put code in there where we were storing all the results into this history here. So we can go and use some code. I use this prompt to make this code to plot the history. And then we can see basically over each epoch from 0 or the first one all the way to the 34th one when it stopped itself, how did the model's accuracy change? So we can see it for the validation accuracy, which is the orange line, which we care more about, and the training accuracy, which is the blue line, which we don't care quite as much about. And so we can see that we had some gains initially in validation accuracy. It was kind of trending upwards and becoming more and more accurate. And then we eventually just got to a point where it was kind of just bouncing around up and down. And then that's when it just decided to cut itself off and stop training anymore. And then with the model loss, right, the number we wanted to be better than was 0.693. That's the complete random guess. So we started off even better, and then we kind of got lower and lower losses and lower losses, and then eventually got to the point where it just bounced around up and down and it cut itself off. So now let's try some more models and see if we can get better, higher model accuracy or lower model loss. So I just tried another experiment where I used a similar type of algorithm, a feed-forward neural network, but we changed a few things, including one of which is the learning rate. So we made the learning rate slower, which means that the model is going to change less between each epoch. So I ran that with this new code, and again, this code can be created with the prompt right here. And so then we can plot the final outputs like this. And one thing you'll notice with this decreased learning rate, like if we look at this model loss on the training loss and the validation loss over each epoch, we can see that it's a more smooth line, right? Because we're not making a ton of changes in between each model. So compare that to our previous model where it bounced around all crazy like this, zigzagging up and down. It's just less changes between each model. And what we will end up seeing here is that the validation loss and the validation accuracy are not going to be very much different from the previous attempt we tried at the feed-forward neural network. So our validation loss in the original run was this 0.6909, remember, lower is better. And now this time we got 0.6911, so we actually did better the previous time. And then the validation accuracy, the first time we ran it was 0.5253, and now this time it was 0.5234. So both were better the first time we ran it. So now I think we should move on to maybe trying a different type of algorithm and switching to a more powerful machine. So we've been running on this machine right here, but we've got like $290 left. So why don't we try switching to more powerful machines and then trying a new type of algorithm, which is going to be a gated recurrent unit, which is going to function a little bit differently. And we're actually going to do it in a specific way as so that it becomes more computationally intensive. And we're going to see if we throw more compute or more computing power at this problem, maybe we can get better results. So I just used AI generated code to test a gated recurrent unit model. And what I actually figured out was that my script or my cloud-based Python application here was not properly using the NVIDIA GPUs. And we didn't really notice it on the past ones because those models didn't require enough computing power to make me notice that those GPUs weren't being used. So I actually went back and looked at the video and I could see that in the past, most of the usage was in the CPU and not in the GPU. So now we've got it flipped. I had to just write a few, I had to write some lines of code at the top to basically make sure it was importing the TensorFlow GPU properly and just configuring it correctly. But now we were good to go. And so I actually ran this now with the GPU working, this third experiment. And so I noticed it wasn't working because it would have taken like weeks for this to run if you only use the CPU. But with the GPU, we can see that my script or my cloud-based Python application here was not properly using the NVIDIA GPUs. It actually only went through 13 different epochs. And what we'll see if we look at the plotted results is we have our model accuracy here. And we'll see here the training accuracy over the 12 epochs that it had run goes up linearly. However, the actual validation accuracy starts off higher and then falls in sort of flat lines. And so we'll see that it actually stopped after the 13 epochs because one parameter that we put in here was this value of patience equals 10, which means that if the validation accuracy has not increased in the last 10 epochs, then just cancel the running job. And so what we'll see is that it was the highest at the third one, and then it never got back to it, and so it canceled there. And then we can also see with the modeling the losses that we see our training loss keeps decreasing as we keep doing more epochs. So the training loss is getting better because with losses, you prefer lower losses. However, our validation loss is kind of flatlined, and then it starts spiking up at the end here. And so what this is showing us is that this is a classic sign of overfitting. We're overfitting on this training accuracy. So on the training data, the model appears to be more and more accurate as we go. However, once we actually test it on out of training set data, the validation accuracy and the validation loss become worse and worse. So what I'm going to do now is actually try to tweak some of the parameters that I have set here to see if I rerun it, will we start to get more accurate results on the data that's not in the training set. So I went ahead and made some changes to the code that should make the model less inclined to overfit. So I'll just quickly tell you what I did, and if you want to read more, you can pause it and see underneath what each one does. So we changed the number of GR units from 64 to 32 to make the model a little bit more simple. We changed these dense units from 32 down to 16 here. And we also increased the dropout rates. And then we also made the learning rate smaller because that's going to help the model converge. So I reran and it took quite a while. And then now we'll see that the training accuracy and the validation accuracy, they actually sort of moved more so together. So we did remove the overfitting issue, and we can see that the validation accuracy, this orange line, got higher and higher generally as we train more, but we still see that we're maxing out around that 52.5% accuracy, which is better than a coin toss, but not a whole lot better. And we can also see the validation loss generally kept gradually declining. So here's where we're at. I think what I'm going to do is I've got about $243 in credits left, and I'm actually just going to take a bunch of time offline to tweak different parameters with the 3 different models we've already created, and also perhaps try some new models and see if I can report back with anything that's getting better accuracy than this 52.5%. And then once I've used up all the credits, what we'll do is actually just figure out which model ended up being the most accurate, and then trying to run that in the paper trading environment to see how it does in terms of generating any profits. So I kept tweaking the parameters of the model, and what I was finding was that I really couldn't find a model that would give a better validation accuracy than about 52.5% for NVIDIA. So then I had a thought, well, maybe because NVIDIA over the last 2 years, which is when we've been pulling the sample data for, has been one of the most traded stocks and probably has some of the most attention on it of any stock from quantitative hedge funds, that any alpha that could be gained by trying to train a model like this on NVIDIA might already have been squeezed out of the market. There might be more market efficiency on that stock because of how much attention has been paid to it by people who are a lot smarter than me with a lot more money than me. So then I thought, why don't I try maybe a different stock? So I actually tried our same models that we've been using on NVIDIA, but this time with a different stock, and all I did was just change the ticker that we're retrieving for the data of SMCI. Now this is super micro computer, and they just they're also in the AI space like NVIDIA, but they do data centers. So they'll build the data centers and the server racks where NVIDIA's GPUs are actually stored. And so we can see that their volume is about 16 million and their market cap is about 25 billion. Compare that to NVIDIA, whose volume was over 100 million and the market cap was 3.5 trillion. So this is a smaller company, a smaller stock, and I thought, hey, maybe there's a way that we can get some, extract some alpha from a stock that people pay less attention to. So all I did was change the ticker and then rerun the models. And what I actually found was that I was able to get some higher model accuracy. So here we have the validation accuracy and I should specify that this right here was this feed forward network with the adjusted learning rate. So let's see how that looks, right? So we're actually getting up to about 53.5% for the validation accuracy, which was about a whole percentage higher than we ever got for NVIDIA. So I'm thinking maybe our move here is to move to different stocks than NVIDIA. So then what I did after that was I did the SMCI data with this gated recurrent unit model. And so now the way I actually ran this was to do 25 separate tests of the model, where we changed the parameters for the tests, like the learning rate and the number of units, etc. And so I had this run through 25 different tests, and this actually took several hours with one of the more powerful Tensor Core GPUs. So this was a massive test on this. It took 2 hours and 11 minutes to do 25 trials. What it ended up actually finding was that the best performing model actually had a validation accuracy. And what it ended up finding was that the best performing model actually had a validation accuracy of 53.8%, so almost 48%. And what it actually ended up finding was that the best validation accuracy we saw from any of the models was 54.1%. So that is very good. The best we ever got with NVIDIA was around 52.5%. So we're getting about a 1.5% better. So basically 54% of the time it's predicting the correct price movement in the validation data set. However, the model is training itself based on how it's performing against the validation data set. So what we really need to look at is the test data set, which is how does it perform on data that it has never seen before. And so what this model ended up doing on the test set was right about 51.4% of the time. Now that's better than 50-50. However, once we have to consider commissions and the bid-ask spreads and possible slippage, delays between when we place an order and when it actually executes, this might not be enough to be profitable. So now what I'm thinking is we're down to about $200 of credits, and I might use another $100 of credits or so to try all these models out on different stocks. So I've got my result for SMCI. Now maybe I'll try as many stocks as I can with these current models until we deplete our credits down to like 100. And then I'll basically go with the one that had the best results with the stock. And then we'll just let it run with the last 100 credits on a paper trading portfolio and see how it actually does. All right, I am back after having done a decent amount of work. So we are now down to about $92 of credit. So I used over $100. And what I did was I actually tested over 200 different models with 8 different stocks. So if I go over to the files over here, we can see that I have all these different stocks like PZZA, JP Morgan, NVIDIA. So in each one of these folders, I can click into it and I can see that I've run 25 different trials where I stored the results of the trial and the parameters of the model. And then I actually saved the model that performed the best for each one. So I ended up using these more complex gated recurrent unit models for all of them. And so I did it on these 8 stocks. So we have Fiverr, which is just a website for hiring freelancers. Lockheed Martin, which is a military defense company. Then NVIDIA and SMCI, which are both in the GPU AI space. JP Morgan, financial space. ExxonMobil, energy, oil space. Pizza, which is Papa John's, so food, and then United Healthcare for the healthcare sector. I wanted to try different stocks from all different sectors of different sizes and different volumes to see if maybe that could affect how we were doing. And then for each of these, I tested 25 different models and stored the result that had the best validation accuracy of all 25. So that's the results you're seeing in this column for each one. And then once you take the best of the 25 models that did the best with the validation accuracy, I ended up using that to find the test accuracy. So this is the most important column because it tells us on data that the model has never seen before and was not trained on or validated on, how did it do? And we see that I stored this from best to worst. So Fiverr actually did the best, and the model was actually able to correctly predict which direction the price would move over the next 5 minutes, 52.72% of the time, which is actually quite a bit better than all of the other stocks. So what we're going to do now is we're going to use the best performing Fiverr model of all 25, and we're going to try to live algorithmically trade Fiverr stock with the paper trading account to see if our account's value goes up in real time or down in real time. All right, we've finally got our model up and running, and now let me walk you through the basic logic of how it's going to function. So first, we're going to take in our data, and we're going to collect the Fiverr trades, and we're doing Fiverr again because that's the one that performed the best in our testing models. And we're going to create a new 1-minute bar every 60 seconds. And then we'll go through the most recent 60 bars, so 1 hour of data, and calculate 26 financial features based on the sequence, like moving averages, volatility, different features like that. And then here's where the AI prediction is going to come in. So we'll feed in our 26 features into the gated recurrent unit model, and then the model will output a single probability, in this example 58%, and this is basically the bot's confidence that the price will be higher in 5 minutes. So if we have a buy probability above 50.05%, then we want to trigger a buy of 1,000 shares of a market order of Fiverr stock in our interactive brokers paper trading account. Now, how did I settle on this value of 50.5%? Well, I actually ran this bot for a few days and I observed the probabilities that it fed out. And the bot is actually performing more conservatively. And so it was only sending a probability of greater than 50.5% a handful of times each day. So I wanted to make the bot set up so that it would only trade a few times a day when it is most confident that the price will be higher in 5 minutes, and then it will shortly after close out the position. So most of these probabilities from this bot are actually below 49.5%. So what's likely going to happen is a few times per day it'll trigger a buy, and then within a few minutes it should close out that position. And I've made the logic so that it won't sell if it has 0 shares. So we can't have a net short position, we can only go back to 0. So I've had the bot functioning for a little over an hour right now. And if we look at each of these signals, so here we have a probability of 0.4845, then the next minute is 0.4981, and basically every minute it comes up with a new probability. And you can see that none of these have exceeded the 50.5% thus far that I've been running it today in the last hour. So we haven't actually executed any trades. And that's by design. We want to be more overall conservative. So if I look at the trade history for the day, we don't see anything happening. So we'll see in this paper trading account today, we have $1,084,601, and that can be our benchmark starting point as I run this bot to see if it really can successfully generate profits. So I'm going to actually probably just keep running this bot as long as my credits will allow. So we're at 23 credits right now. The company that sponsored this video, Datalore, that runs this notebook, they've generously given me some coupon thing I can use to get like 200 more credits. So I'll probably throw those in there, and then we'll just keep running it for a few days, and I'll touch back to see if this balance ultimately ends up going up or down. I ran the bot for 3 days, and now I have the results, and they're not as great as we may have hoped, and I have a reason why. So basically, we started off with $1,084,601. Then I let this bot run for a few days, and we ended up with $1,083,718 for a loss of $883. And again, remember that this is paper trading money. So we can see here in the trader workstation that now this is our value after running this bot for 3 days. And let's get into what happened. Why did this bot lose money in this way? The main reason that this bot lost money was because of the bid-ask spread. Specifically, that my training data did not account for the bid-ask spread. It just had one price for every minute, and it didn't tell you what was the bid and ask for each minute. So we were training the bot on just a single price, and then it was guessing in the next 5 minutes whether it would go up or down. But that didn't count for the fact that with any stock, you can buy it for more expensive. Like right here for Fiverr, we have an ask of $29.18 and a bid of $29.14. So we can only, if we just bought and sold this immediately, we would lose 4 cents on this spread. So in order to make up for that, the bot's prediction accuracy would need to be even higher than the, I think, 53% that we might have had, or you would need to train the bot on data that includes the bid-ask spread. I think in hindsight, I would make sure that my data source has bid-ask spread, and then my orders would not be placed at the market. So I wouldn't hit this, let's say 29.18 or this 29.14. Instead, place limit orders that's right between the bid and the ask spread. So I'm trying to trade right in the center each time. And I'll show you an example to articulate. So basically, this bot opened up this position. It bought 1,000 shares of Fiverr at 29.45. And then 1 minute and 2 seconds later, it sold all shares right there, sold at 29.23. So on this image here, I was showing you this 4 cent spread. But at that time, this bot actually had a spread that was closer to 22 cents. So really, this bot buying and selling at the market was literally just losing the full bid-ask spread. So where do we go from here? Well, I'm gonna make all the code written in this video free, so you can go down to the link in the description to download it. And I think if anyone wanted to play with this, what they would be best served to do would be to find a data source that uses the bid-ask spread, and then try to orchestrate a bot that places orders at the limit between the two, limit orders between the bid-ask spread, so that you're not chewing up that bid-ask spread each time. Additionally, I would encourage you to sign up for free to try out the software that I use in this video to do all this coding with the AI, which is Datalore. And they have provided the viewers of this video with a promo code for 50% off if you want to get any higher tiers of the subscriptions with this code Analyze Like Ryan. Thank you for watching the video, and even though we weren't successful creating a profitable trading bot, I hope you at least took something away of value.